imagine for just a second that you are walking through your living room in the dark, right? And you completely, just brutally stub your toe on the edge of a heavy coffee table.
Oh, yeah. The absolute worst.
It is. Or, maybe you are one of the millions of people who wake up every single day dealing with this dull, persistent, chronic ache in your lower back.
Right.
When that sensation hits you, you almost certainly assume that the experience of that pain is happening entirely in your brain. Like you figure your toe or your back just sends a basic dumb alert signal up a biological wire, and then, your brain does all the heavy computational lifting to actually make it hurt.
Yeah, that's the standard assumption.
Right. But what if we've been looking at, the entirely wrong map of the human nervous system for decades?
I mean, it is a massive paradigm shift because for the longest time, the broader field of neuroscience really did view the spinal cord as just that passive wire.
Just the cable.
Exactly. A biological Ethernet cable, if you will, whose only job was to blindly relay physical signals from the body up into the skull. But the research we're looking at today completely shatters that assumption. We're learning that the spinal cord is actually doing a tremendous amount of thinking on its own.
Okay, let's unpack this, because today's deep dive is into a truly groundbreaking paper. This was published in Cell Reports Medicine in December 2026.
Yep.
And our mission today, the whole goal of this deep dive, is to figure out how a team of scientists created something called the Corticospinal Pain Intensity Pattern, which we're just going to call CsPIP to keep things simple.
Good call. CsPIP is much easier.
Right.
Yeah.
And this model, it essentially proves that pain is a highly active two-way street between the brain and the spinal cord. We're going to trace exactly how researchers figured this out, starting with healthy volunteers getting exposed to intense heat pain, all the way to patients suffering from chronic irritable bowel syndrome who are getting electroacupuncture.
Right. And to really appreciate why the CsPIP model is such a revolution, we kind of have to look at the outdated model it's replacing.
The old way of thinking.
Yeah. Historically, everything was focused on what researchers called the pain matrix. The prevailing dogma was that nociceptive signals, those raw, unfiltered danger signals from a burn or a cut, they just travel up the spinal cord and terminate in very specific regions of the brain.
Okay.
We're talking about areas like the insula, the dorsal anterior cingulate cortex, the thalamus, and the somatosensory cortices.
Okay, let me pause you right there, because you just dropped a lot of heavy anatomical names.
I did, yeah.
For those of us who aren't neurosurgeons, what are those specific brain regions actually doing when that danger signal first arrives?
Fair enough.
Yeah.
So think of the thalamus as the central router.
Like a switchboard.
Exactly. It takes the incoming raw signal and decides where to send it in the brain. It sends it to the somatosensory cortices, which we usually just call S1 and S2. And those act like the physical map of your body. They're the parts that tell you, hey, the damage is exactly on the left big toe.
Got it.
Then it sends the signal to the insula, which processes the visceral sort of emotional feeling of being hurt. And then the dorsal anterior cingulate cortex, or DACC, that basically acts as the alarm bell. It's telling you to pay attention and do something about it.
Wow. Okay.
And the consensus was that these brain areas alone stitch together those signals to produce the subjective feeling you call pain.
But, if you think about it, isn't focusing entirely on those brain regions like trying to understand how a massive car factory works by only looking at the CEO's office?
Yes.
If you completely ignore the assembly line on the floor, you are missing where all the actual building and modifying is happening.
That is a highly accurate way to look at it, actually. The spinal cord is that assembly line. It is the very first site of integration in your central nervous system. Okay.
And what's fascinating here is that this new research proves the spinal cord is actively processing, filtering, and modifying the information before the brain's CEO ever even sees the report.
So how did they actually prove that? Because getting data on this, it isn't easy, right? I know they focused on the cervical spinal cord, which is basically the neck area, using functional MRI.
Right, fMRI.
And fMRI, it measures changes in blood flow to see which neurons are firing. So when they applied painful heat to a participant's forearm in the scanner, they didn't just look at the brain, they looked right at the C6 vertebral level of the neck.
Yes, and what they observed there was incredibly highly organized activity.
Really?
The spinal cord wasn't just lighting up uniformly. They saw positive activation in the dorsal horn. Now that is the back part of the spinal cord, which acts as the sensory inbox where signals from the body first enter.
Right, sensory inbox, dorsal horn.
Right. But at the exact same millisecond, they observed negative activation in the ventral horn.
Wait,
Yeah.
negative activation, what does that actually mean in this context? It means suppressed neural activity. The ventral horn is the front part of the spinal cord, and traditionally it handles motor signals, the outbox that tells your muscles to move.
Oh, wow.
So this simultaneous positive sensory firing and negative motor suppression, it represents an active gating mechanism.
Gating.
Yeah. The spinal cord is locally computing the threat. It is actively turning the volume up on the incoming sensory data while momentarily suppressing the outgoing motor response. It's essentially editing and prioritizing the pain signal before sending it upstairs.
So the spine is literally opening and closing physiological gates.
Exactly.
Is amplifying or dampening the pain signal all on its own.
Yes, it's a localized computational hub.
So let's lock this in for a second. Mini summary 1. Pain is encoded by a dynamic interaction between the brain and the spinal cord, not just the brain alone.
Perfectly said.
So here's a question for you listening right now. Audience question 1. Think about the last time you were in serious pain. Does it change how you view your own discomfort, knowing that your spinal cord was actively editing that feeling before it even reached your conscious mind?
It completely reframes our understanding of human physiology, I think.
Yeah.
But, knowing this and actually measuring it to build a model are two very different things.
Right, because this two-way dialogue, it presented a massive technical hurdle. The spinal cord is incredibly narrow, right? It's roughly the width of your little finger.
Here is tiny.
And it is encased in dense bone, and it shifts slightly every single time you take a breath or your heart beats.
It's constantly moving.
So trying to get a clear, functional MRI image of the brain and that tiny moving spinal cord at the exact same moment, that sounds like an absolute nightmare for a radiologist.
Oh, it was considered nearly impossible until very recently. In the past, studies would scan the brain and then they'd scan the spine separately.
Oh, I see.
But doing that introduces a time lag. You can't see the real-time conversation between them. The breakthrough in this paper was their ability to take 330 simultaneous fMRI scans of both the brain and the cervical spinal cord.
330 at the same time.
At the same time. By capturing them concurrently, they caught the precise physiological coherence. They could see the exact millisecond the spine gated the signal and the brain received it.
But that creates a whole new problem, doesn't it? If you take 330 simultaneous scans, you are generating millions and millions of data points, voxels, right?
Mm-hmm.
Which are basically 3D pixels of brain activity.
Correct.
How does a human researcher find the specific pattern of pain hiding in that absolute mountain of static noise?
Well, they don't. A human couldn't possibly process that much simultaneous data. They had to use a highly advanced machine learning algorithm called lasso PCR.
Okay, you're going to have to translate that for me.
Yeah.
Lasso PCR sounds like, I don't know, a rodeo event for geneticists. What is the algorithm actually doing under the hood?
Right, so it stands for least absolute shrinkage and selection operator combined with principal component regression.
Wow. Oh.
I know, it is a mouthful, but the mechanism is actually quite elegant. When you have millions of voxels firing in an fMRI, most of it is irrelevant noise.
Mm-hmm.
Is your brain regulating your breathing? Or maybe you're thinking about what you'll have for lunch, or it's just random neural static.
Right.
The lasso part applies a mathematical penalty to the data. It forces the computer to shrink the value of all those irrelevant, noisy data points down to absolute zero.
Yeah, I picture it kind of like a hyper-efficient, ruthless detective walking into a massive, chaotic crime scene.
I like that.
Like instead of interviewing all 10,000 people in the crowd, the detective literally lassos the exact specific combination of clues, both the positive firings and the negative suppressions, that mathematically predict how much pain a person is in. And it completely tosses everyone else out of the room.
That is exactly how it functions. It isolates the principal components. And to train this detective, this was study 1, the researchers used healthy participants. They attached a thermode, which is a small computer-controlled metal plate, to their forearms.
Mm-hmm.
They started at a comfortable baseline of 32 degrees Celsius, which is about 89 degrees Fahrenheit, and they slowly ramped the heat up to a painful level.
Ouch.
Yeah. And as the participants rated their pain, the algorithm learned exactly what that increasing intensity looked like across the entire brain-spine network.
But I mean, how do we know the algorithm didn't just learn to recognize when a human is feeling anything super intense? Because if I get really cold or feel a terrible itch, my brain lights up too.
Yeah.
Did they test if this model was actually specific to physical pain?
They absolutely had to test for specificity. That was studied too. They applied a combination of histamine and a cooling stimulus to the skin of the participants to create this intensely uncomfortable, agonizing itch.
Ugh, I can feel that just thinking about it.
It is highly distracting and it creates massive neural activity. But when they mapped the CsPIP model's predictions, the results were definitive. When tracking the painful heat, the algorithm's calibration curve perfectly tracked a straight line, matching the human subjective rating. As the heat pain went up, the model's output went up in lockstep. But for the intense itch, the model's response completely flatlined.
Really?
Yeah, it threw all that itch data out as noise. It knew the difference.
That is wild. And they pushed it even further, right? Because they wanted to know if it could tell the difference between my physical pain and the pain I feel when I see someone else get hurt.
Exactly. The empathy test, study 4.
So they put participants in the scanner and had them watch videos of someone else receiving a painful electric shock. And we all know that sympathetic cringe, right?
Yeah.
That phantom sting you get when you see a bad injury.
Oh, yeah. Your brain's empathy networks light up like fireworks.
But did the brain-spine model register it as pain?
0. Nothing at all. Which tells us something crucial about the underlying mechanism here. The CsPIP model isolates somatic physical pain. The emotional pain of empathy might feel real to us psychologically, but biologically, it doesn't utilize that specific corticospinal gating dialogue.
Okay, so that leads us to mini summary 2. The CsPIP is a highly specific machine learning-derived pattern that tracks actual physical pain, and it completely ignores itchy sensations or the emotional pain of seeing someone else get hurt.
Exactly right.
So audience question 2 for you. If this algorithm can perfectly distinguish between your physical pain and your empathy for someone else's pain, what other subjective human experiences do you think we might soon be able to decode from a brain-spine scan?
Potential is staggering.
Okay, we're about 5 minutes in, so let's do a quick recap of where we are for you, the listener, to hit our first milestone.
Sounds good.
Bullet 1. The old brain-only pain matrix is outdated. We need a corticospinal view, which means brain plus spinal cord. Bullet 2. Researchers used a machine learning tool called Lasso PCR to build the CsPIP model based on simultaneous brain and spine fMRI scans.
Yep.
And bullet 3. The model is incredibly specific. It knows exactly when you are in physical pain versus when you are just icky or feeling empathetic.
Perfect summary.
Okay, so moving on. We know the model works for a hot metal plate, but, heat pain is just one type of pain. What if you touch a live electrical wire? Does the spine treat it differently? Because here's where it gets really interesting.
It does. To find out, they ran study 3. They applied painful electrical stimulation to the participants' forearms. Now, you have to remember, the CsPIP algorithm had only been trained on heat pain up to this point.
Right, it had never seen electricity.
It had never seen electrical pain data, yet when they fed the electrical fMRI data into the model, it successfully predicted the intensity of the electric shocks.
So the signature just generalized. The fundamental biological machinery for pain is the same, regardless of the weapon.
Precisely. Yeah. Modality independence. And to understand why this matters, they retrained a brand new model just for the electrical pain and compared it to the heat model.
Right.
They analyzed 275 different regions across the brain. Out of those, 81 specific regions showed significant overlap between the heat pain and the electrical pain.
Okay, and I looked at the paper, and I found the functional mapping of those 81 overlapping regions absolutely fascinating.
Yeah.
Because when you look at what those specific brain areas actually do on a daily basis, they aren't just raw sensory detectors. They map to deep terms like perception, vision, and cognition. But wait, why would my brain need my visual cortex or my complex cognition networks to process getting a raw electric zap on my arm?
Because the brain is constantly contextualizing the threat. Pain is not just a measure of tissue damage, it is a measure of perceived danger.
Right.
Your vision and cognitive networks are engaged because your brain is mapping the environment, it's trying to see the source of the shock, assessing how to escape, and calculating if the threat is ongoing.
So it implies that the core signature of human pain is heavily processed and filtered through our cognitive and perceptual filters.
Exactly.
Which brings us to mini summary 3. The corticospinal signature for pain is universal across different types of physical threats, and it shares deep neural architecture tied to human cognition and perception.
Well said.
And here is audience question 3. Since cognitive networks heavily overlap with pain networks, how much of the pain you feel do you think is driven by the physical injury versus how your brain is actually paying attention to it?
That entanglement is the ultimate puzzle, really, of mind-body medicine. And it naturally leads to the next massive hurdle for the model.
Right, because we've proven the algorithm can track the pain signal going up the spinal cord.
Right.
But can it track pain relief coming down?
Exactly.
This brings us to the 10S test. Now, 10NS stands for transcutaneous electrical nerve stimulation. If you've been to physical therapy, you've probably seen those little portable machines with sticky pads that send a buzzing sensation into sore muscles.
Yep, very common.
So they introduced a case from study 1. They had healthy participants in the scanner and applied 10NS therapy to their left forearm.
Right, and they split them into 2 groups to control for the placebo effect.
Okay.
One group got active 10NS, so 100 hertz electrical buzzing that feels strong and vibrating, but it's not painful. The other group received a sham treatment. It was fake. The pads were stuck on their arm, the machine beeped, but no actual electricity was delivered.
Okay, before we get to the algorithm's results, if we connect this to the bigger picture,
Yeah?
how does a buzzing sensation actually relieve pain biologically? What is the actual mechanism of relief there?
Okay, so it works by interrupting the nociceptive signaling at the dorsal horn of the spinal cord.
The inbox.
Right. It utilizes the gate control theory. The buzzing sensation activates large, fast beta-touch nerve fibers. These fast-touch signals race to the spinal cord and literally crowd out the slower pain signals, physically closing the gate.
Wow.
And at the exact same time, the brain perceives this safe buzzing and activates descending inhibitory pathways.
Meaning it sends signals down.
Yes, from the brainstem back down the spinal cord to release natural painkillers directly onto the spinal neurons.
So it blocks it from the bottom up and the top down. Did the CsPIP model actually see this happening?
It did. The algorithm perfectly tracked the reduction in pain, but only on the treated left arm of the active group.
Only the left arm.
Right. The untreated right arm showed no change, and the sham group, the people who just thought they were getting treated, showed absolutely no change in the model either.
This is a huge deal because older brain-only models like the neurologic pain signature, or NPS, and CsPIP, they often failed this test.
They did?
Because older algorithms tracked the cognitive expectation of relief, the placebo. Because the patient expected to feel better, the brain shifted. And older models would falsely register that as pain relief. But this new model proved it was tracking actual physiological gating at the spinal level.
It isolates true biological relief from cognitive expectation.
Okay, mini summary 4. CsPIP is sensitive enough to act as an objective biomarker for pain relief, proving whether a physical intervention like TNS is genuinely blocking pain signals at the spinal cord.
Exactly.
And audience question 4 for you. If we now have an objective pain thermometer that basically can't be tricked by the placebo effect, how should this change the way we test new painkillers?
It should revolutionize clinical trials, honestly. It removes the subjective guesswork entirely.
Okay, we are about 10 minutes in. Time for our second 5-minute recap to lock this in.
Let's do it.
Bullet 1. The CsPIP model works for multiple types of pain, like heat and electrical sharing networks linked to our cognition.
Yeah.
Bullet 2. The model successfully tracked real-time pain relief from 10NS therapy.
Right.
And bullet 3. It proved that 10NS actually physically blocks pain at the spinal level, separating biological relief from the placebo effect.
Spot on. But, up to this point, there's a massive caveat we have to address.
What's that?
All of these tests were conducted on healthy, normal people experiencing acute temporary pain. They were just getting briefly zapped or burned in a highly controlled scanner.
Right. And that is not what most people suffering from pain are actually dealing with. So what does this all mean for a real patient? What happens when the pain is chronic, internal, and it just never turns off?
To answer that, they ran Study 5. The researchers brought in 83 patients suffering from irritable bowel syndrome, or IBS.
Okay.
IBS is a classic visceral, meaning internal chronic pain condition. The pain is deep within the gut, and it is persistent.
But the methodology has to change here, right? Because you can't trigger a sudden reaction with a hot piece of metal for these patients. They are just lying still in the MRI scanner, resting, experiencing their daily baseline of chronic discomfort. So how do you measure a signal when there is no sudden shock to track?
Right. They had to use a neuroimaging metric called FALFF.
FALFF. Let me guess, another dense technical mechanism.
It is, yeah. It stands for fractional amplitude of low-frequency fluctuations.
Oh, boy.
But the concept is very logical. When you are just resting, your brain and spinal cords still have spontaneous activity. FALF simply measures the intensity of those low-frequency resting signals.
Okay. I picture it like the engine of a car. If your nervous system is the engine, FALFF is basically measuring the idling speed.
That's a great analogy.
Like even when your foot is completely off the gas pedal, meaning there's no acute pain stimulus happening, the neural engine in a chronic pain patient is revving way too high. The baseline hum of their system is elevated.
Exactly. So the researchers measured this elevated baseline hum in the IBS patients. And then the treatment phase, the patients underwent 18 sessions of electroacupuncture over 6 weeks.
Wow, 18 sessions.
Yeah, specifically targeting an acupoint on the leg called Zuzanli, or ST36, which is known to modulate gut pain.
Okay, and I saw the researchers added a brilliant layer of analysis here. They used a mathematical grouping tool called K-means clustering to divide the IBS patients into 2 groups based on their psychological symptoms. So they had a high-burden group and a low-burden group. And when they fed the data into the model, the algorithm brilliantly predicted the baseline pain and tracked the treatment-induced relief over 6 weeks, but specifically only for the low-burden group.
Yes, this is a vital distinction.
Which brings us to mini-summary 5. The model works on chronic resting pain by measuring the baseline hum, the FALFF of the nervous system, and successfully tracked long-term pain relief from electroacupuncture.
Correct.
And audience question 5. The model worked best on patients with a lower psychological burden. So does this suggest that for some patients, the mental and emotional weight of chronic pain eventually overrides the physical spinal signals?
It strongly suggests exactly that. In patients with severe psychological burden, the cognitive and emotional dimensions become the dominant source of suffering. A purely physical spinal signature just can't fully capture their reality anymore.
That is so profound. But, I want to push back on the premise of this specific test for a second.
Okay, go ahead.
Measuring a static average baseline hum is great, but human brain activity isn't a static hum. It isn't a flat line. It is constantly shifting and fluctuating second by second.
And this raises an important question, and the researchers anticipated that exact critique. A static veer isn't enough. So they introduced the final and arguably most mind-bending piece of the puzzle, the hidden Markov model.
Okay, hidden Markov model, HMM. What does that actually do?
The HMM parses brain activity into discrete, recurring states over time. It doesn't look at static averages. It assumes the nervous system moves through distinct hidden phases, millisecond by millisecond.
So sticking with the car analogy, it's like a transmission system. And the HMM revealed that the corticospinal network essentially has 5 different gears or states.
Yes, 5 states.
State 5 is a pro-nociceptive state. It's high gear. It is amplifying the pain signals.
Yeah.
But state 1 is an anti-nociceptive state. It's a neutral gear, calming things down.
Exactly. And this reveals the dynamic mechanism of chronic pain. The static hum we discussed earlier, it actually happens because chronic pain patients suffer from a temporal bias.
The temporal bias.
They are getting locked into state 5, the pro-nociceptive state, and failing to transition back into state 1.
Yeah.
Their biological transmission is literally stuck in high gear.
So they just can't shift down.
Right. A healthy system shifts back and forth. A chronic pain patient system is trapped in a recurring pro-pain brain-spine state.
Okay, mini summary 6. Chronic pain isn't just a volume knob turned up. It's a dynamic system getting trapped in a specific recurring pro-pain state.
Beautifully summarized.
And our final audience question, question 6.
Yeah.
If chronic pain is a matter of getting stuck in a specific neural state, what habits or therapies do you think might act as the clutch to help your nervous system finally shift gears?
It's the multi-million-dollar question.
So let's bring it all together for a final synthesis. We've moved from viewing pain as this brain-only experience to understanding it as a dynamic, shifting dialogue between the cervical spinal cord and the brain. Right.
We have a machine learning model, the CsPIP, that can objectively measure this. It can track acute relief and even map the stuck gears of chronic visceral pain.
And, I'd leave the listener with this final paradigm shift.
Yeah.
Knowledge is most valuable when understood and applied. If our pain is a combination of spinal gating and brain processing, future treatments might just bypass the brain entirely.
Really?
Yeah. Imagine a targeted therapy like highly specific spinal cord stimulation designed not just to block a pain signal, but to physically force your spinal cord to shift gears out of a pro-nociceptive state.
Wow. It really feels at the beginning of a whole new era of medicine. Thank you so much for joining us on this deep dive. And for you listening, the next time you feel a twinge of pain, try to think differently about the signals racing up and down your own spine. It's not just a dumb wire. It's an active system. Until next time.